So today we will discuss the large signal analysis. Last meeting we have discussed the basic differential pair, and this differential pair have a great advantage compared of implementing a single stage amplifier because this has a greater immunity to noise, because it will cancel the noise, and it has higher voltage swing. Also, we also discussed what is the advantage of adding this tail current here and what does it implies. And also we have discussed the maximum or the range of input common mode that would make this differential amplifier work properly, what is the maximum and minimum input of this differential amplifier. Beyond that, this differential amplifier will not work properly. And also, in our differential amplifier pair that we have discussed earlier, we have predefined what is our, the characteristic of, or what is the output of the voltage with respect to Vn1 and Vn2 when our Vn1 is very much greater than Vn2 and something like that. So actually last meeting I already show you the, let me use the red one. Okay, so we already derive what is the change of V out with respect to input, this figure here. So whenever our Vn1 is very much greater than Vn2, and in this case our drain current here, the ID1, would be very much greater than ID2 and would approximately equal to ISS, and our ID2 here would approximately equal to 0. So in this side, so giving us VO1 equal to VDD minus ID1 RD, or VDD minus ISS RD. And for our VO2, we will have ID2, my mistake. This would be, since this is open circuit, this would be VDD. Okay, so this would be VDD. So if we're going to compute the difference between VO1 minus VO2 whenever Vn1 is very much greater than Vn2, we'll have negative ISSRD. And we have this. And same is true when our Vn2 is very much greater than Vn1. So kabaliktaran lang sila. Then we will have the RDISS. And in that case, our ID1 in that will have equal to 0 and our ID2 is equal to ISS. And our VO1 minus VO2 in that case is equal to RD times ISS. So now, what are we trying to solve here is what would be the value of the, you know, what is the value of our VO1 and VO2 with respect to VN1 minus VN2 when our current is not in maximum if nandito lang siya. Ano ba ang characteristic ng VO1 minus VO2 natin with respect to VN1 minus VN2? So in order to solve that, let us go back here. So in order to get the characteristic of the change of V out with respect to change of V in, or the V in 1 minus V in 2 in between, so let us first consider again when our ID1 is equal to ISS and our ID2 is equal to 0, and vice versa. But let us say we have this condition first. ID1 is equal to ISS and ID2 is equal to 0. So applying KVL here, let us say in V in 1, we have V in 1 and we have this VGS, VGS1 here. And we have our BP here. So by KVL, let's say this is our loop 1 and this is our loop 2. So applying KVL at loop 1, KVL, Kirchhoff's voltage law at loop 1, we will have V in 1 minus VGS1 is equal to VS. Baka kayo nalito. We can say first we have negative V in 1 plus VGS1 plus VS is equal to 0. And arranging that, we will get this value here. And for KVL2, we have same method. So we'll have VN2 minus VGS2 is equal to VS. So let's say this is equation 1 and we have equation 2. So by reflecting and looking at equation 1 and 2, we can say that V in 1 minus VGS1 is equal to VN2 minus VGS2, since these two equations is equal to VS. So this just equate to each other. So to find VN1 and minus VN2, we must find, we must consider first the drain current, this condition and this condition. But first, we can rewrite this equation into V in 1 minus V in 2 is equal to VGS1 minus VGS2. So in order for us to find the characteristic of V in 1, where this V in 1 minus V in 2, with respect to change of V out or the change of the ID1 and ID2, we must first find what is VGS1 and VGS2 at this condition, So what would be the value of our VGS1 when our ID1 is equal to ISS? And what would be the value of ID2 when what would be the value of VGS2 when our ID2 is equal to 0? So in here, this VGS1, when we say this is in saturation, so VGS1, again, let us review what is the drain current equation before having the VGS, the gate to source voltage. So we know from the fact that the drain current equation is equal to 1/2 mu n COX WL times VGS minus VTH squared. So solving for VGS, for in this time we could solve for VGS1. So by quadratic formula, we could have VGS1 is equal to square root of 2ID mu n COX WL plus VTH. Kindly derive na lang. But if you simplify, you will get this one. So that is for VGS 1. How about for VGS 2? Note that in this drain current equation, we consider that there is no channel length modulation. Okay, so we'll proceed when our ID2 is equal to 0. So we know that in saturation, the gate to source voltage must be greater than VTH. And it would greater than or equal to VTH. And at the edge of conduction, when our MOSFET is about to turn off, nag-start siya nung VGS is equal to VTH. So now, so ito yung kung nagto-turn off na siya, nag-start na siyang turn off in this MOSFET, then our VGS2 is equal to VTH. At this condition, yung nag-start na siyang nag-turn off. So, our VN1, let's use another color to emphasize. Yeah. Our VN1 minus VN2 is equal to square root of 2 ID1. In this case, this ID1 is just equal to ISS. So let's just replace that with ISS. So let's replace that with ISS. So we'll write ISS over mu n COX WL plus VTH, close open parenthesis, and our VGS2 is equal to VTH. So this will just cancel. So our Vn1 minus Vn2, when our drain current ID1 is equal to ISS and ID2 is equal to 0, in this condition only happens when our Vn1 is very much greater than Vn2, right? So Vn1 minus Vn2, in that case, we'll have 2 ISS mu n COX WL. And this ISS over mu n COX WL is actually the overdrive voltage of our MOSFET. This one. This one is the overdrive, VOV. So in that case, our Vn1 minus Vn2 actually is Vn1 minus Vn2 could be written as square root of 2 times the overdrive voltage. So in that condition, when our ID1 is equal to ISS and ID2 is equal to ID2, or Vn1 is very much greater than Vn2. So in the condition that when our Vn1 is very much greater than Vn2 and our ID1 in here is approximately equal to ISS and our ID2 is equal to 0, we can get from our derivation earlier that Vn1 minus Vn2 in that condition is equal to square root of 2 overdrive voltage. So if I have to draw the characteristic of our change of Vn1 with respect to ID1, let me use this figure. I can have, sensya na, masyadong matuwid. Okay. Masyado namang matuwid ang drawing mo, Ma'am Rean. Okay. If I have to draw that line, isipin nyo na lang na straight siya. So this one is Vn1 minus Vn2 when our Vn1 is very much greater than Vn2, then our ID1 is approximately equal to, let's say our ID1 is red. This one, let's say this is red. Medyo pakurba yan ha. Isipin nyo na lang. And then our ID2, let's say, we have blue. We have blue. So ito yung ISS over 2, let's say. Yan yung ISS over 2 natin. ISS over 2. So, ID1 is approximately equal to ISS and our ID2 is equal to 0 here. Approximately 0 ha. 0 yan. Okay. In that case, our voltage in that scenario here, it says from our derivation that it is equal to square root of 2 VOV. And In the case when our Vn2, yung kabaliktaran naman, hindi ko na ipapakita sa inyo, pero ang value na is kabaliktaran din. So, when our Vn2 is very much greater than Vn1, and our ID1 is approximately 0, and our ID2 is equal to ISS, the Vn1 minus Vn2 in here is equal to negative square root of 2 VOV. So, when this case, when our ID2 is equal to ISS, our voltage in here is equal to square root of 2 over drive voltage. So whenever the case when our drain current of either the MOSFET, this would involve our range of the output voltage in which ito yung maximum and minima ng ng input differential pair para mag-operate siya in this region. So now, nakuha na natin yung parang the characteristic of our output voltage with respect to input voltage. So whenever this maximum, pinaka-sukdulan, pinaka-extreme na values ng ID1 and ID2 natin. So now, we will try to solve ano ba ang characteristic nitong portion na ito. Itong portion na ito. When our ID1 and ID2 is almost equal. So, in that case, paano to? Itong naka-shade na ito. Dito. Yung na-yellow na part. Yun ang itatry nating kunin. So, let's use another page. So, in order for us to solve this behavior or the characteristic of the output voltage with respect to Vn1 minus Vn2 in this region, in which we can assume that our ID1 is equal to ID2, in which in that case we have Vn1 minus Vn2 from our discussion earlier by KVL. Vn1 minus Vn2 is equal to VGS1 minus VGS2, and when we are in saturation, both have the drain current ID1 and ID2 equal to ISS over 2, in which they are almost equal. So our VGS1 in that case in saturation will have square root of 2 ID1 mu n COX WL plus VTH. And same goes to our VGS2 will have 2ID2 mu n COX WL plus VTH. So if we have to subtract the two, our Vn1 minus Vn2 is equal to VGS1 minus VGS2. So we'll have Vn1 minus Vn2. Subtracting the two, VGS1 minus VGS2, this would cancel. So what we have left is equal to 2ID1 mu n COX WL minus square root of 2ID2 2 mu n COX WL. So in order for us to really get the characteristic of the change of output voltage with respect to input voltage, we must solve this ID1 and ID2 in terms of a voltage. So in order for us to get that, we must simplify this equation. So simplifying this equation, so let's continue. So we have this Vn1 minus Vn2. Square na lang natin to para mas madali. So squaring that both terms, so we have Vn1 minus Vn2 squared. And hindi ko pa na-simplify ito. So simplifying these two terms, we'll have square root of 2 mu n COX WL times square root of ID1 minus square root of ID2. And this is a square since we already squared this one. So squaring both sides, so we'll have Vn1 minus, lagyan natin sa baba. So what we'll have, we have Vn1 minus Vn2 is equal to square this one, so we'll have 2, right? Mu n COX WL. And we have square root of ID1 minus square root of ID2. Square that. And if we square that, we'll have, remember this property, A minus B squared. We'll have A squared plus B squared minus 2AB. So applying that, we'll have ID1 plus ID2 minus 2 square root of ID1 and ID2. Okay? So, to simplify it further, para ID na lang ang matira. Pero, wait muna. Bago natin ilipat doon, we all know that this ID1 and ID2 is just equal to ISS. So, we can write Vn1 minus Vn2 squared is equal to 2 mu n COX WL times ISS minus 2 square root of ID1 and ID2. Okay? Yun. Okay. ISS minus 2 square root of ID1. So, itong term na to, lagay natin dito sa left side. So, we'll have 1/2 mu n COX WL times Vn1 minus Vn2 squared. Natira na lang ISS minus 2 square root of ID1 and ID2. Yun. So simplifying it further, we can transfer this ISS into the left side. So we'll have 1 half mu n cux wl vn1 minus vn2 squared minus ISS equal to negative 2 square root of ID1, ID2. Okay? So we'll try to get rid of the negative sign. So we multiply this both sides by negative. So we'll have this positive na to. Ito magiging negative. So yun. So we'll have ISS minus 1 half mu n cux wl times vn1 minus vn2 squared. Yun. So let's square natin both sides. So square natin both sides. So we'll have masyadong makulay na talaga. So we have ISS squared and then minus minus 1/4 lang. So we'll have 1/4 mu n cux wl vn1 minus vn2 to the fourth, and this one here must be squared and plus. Okay, so we'll have minus 2 ISS 1 half mu n cux wl vn1 minus vn2 squared. Okay, nakuha ko ba? Let me check. 2 ISS 1 half mu n cux wl times vn1 minus vn2 squared. Squaring it, so we'll have 4 ID1 and ID2. Okay, so with that, actually this 4 ID1 and ID2 can be expressed in this manner. This, let me take note here. Let me give a note. Note that for ID1 and ID2 can be written as ID1 plus ID2 squared minus ID1 minus ID2 squared. So simplifying it, we'll have ID1 squared plus ID2 squared minus plus 2 ID1 ID2 minus ID1 squared plus ID2 squared minus 2 ID1 ID2. Okay, so this one ID1 and ID2 would cancel, and what we have 2id1, id2 minus negative 2id1 and id2 is just equal to 4id1 and id2, which is just equal. So this value here prove that this is equivalent. And this id1 and id2, we know that can be represented as ISS. So 4id1 and id2 could be written as ISS squared minus id1 minus id2 squared. Okay, so we'll try to substitute that in this equation in the next slide. Masyado nang puno ang this slide na to. So earlier we have just get this equation, and in the previous slide we have this 4id1 and id2 could be written as ISS squared minus id1 minus id2 squared. So if we are going to substitute that, let's try to substitute that here. We'll have ISS squared minus 2 ISS. So this one will just cancel, right? So let's leave this as ISS. Okay, so we'll have ISS squared, ISS, mu and CUX WL VN1 minus VN2 squared. Excuse me. So that one, and we'll have 1/4 mu and COX WL, this is squared, and we have VN1 minus VN2 to the power of 4 is equal to ISS squared minus ID1 minus ID2 squared. And this ISS here would cancel. And what we have left is negative ISS mu n CUX WL VN1 minus VN2 squared plus 1/4 mu n CUX WL squared VN1 minus VN2 to the power of 4 equal to negative ID1 minus ID2 squared. And if we are trying to negate all the negative signs, so multiply all by negative, so we'll have this positive, and this one is negative, and this will become a positive. So we have positive ISS mu n CUX WL times VN1 minus VN2 squared minus, erase na lang natin itong positive para hindi tayo ma-confuse. Okay, and that one, mu n CUX WL squared VN1 minus VN2 to the power of 4 time equal to ID1 minus ID2 squared. And yun, and we are going to have same like terms para ma-simplify pa siya further. So we'll have 1/4 mu n CUX WL, itong value na to, times Vn1 minus Vn2 squared. So, kapag i-divide natin to dito, so we'll have 4 ISS mu n cux WL. And that one, and here we'll have ito makakancel na to. So what we'll have minus Vn1 minus Vn2 squared, okay, equal to ID1 minus ID2 squared. So if we are going to extract and get the value of ID1 minus ID2, we have to square root both sides. So we'll have lagay natin to dito sa left side, lagay natin to sa right side. So what we have left is ID1, kung i-square natin, square root rather, ID1, ID2 is equal to yung square niya, kung square natin to, so we'll have 1/2 mu n cux WL Vn1 minus Vn2, then square root nitong value ito. So 4 ISS mu n cux WL minus Vn1 minus Vn2 square. Okay? So we have the value of ID1 minus ID2 is equal to 1/2 mu n cux WL Vn1 minus Vn2 and 4is over mu n cux WL minus Vn1 minus Vn2. And yun, nakuha na natin yung ID1 and ID2 in terms of Vn1 and Vn2. So later we'll have the the value of the output voltage with respect to input. So first, let us remember that the differential output voltage VO1 minus VO2 in terms when our ID1 is equal to ID2 approximately, actually we'll have RD or the R times ID1 minus ID2. So therefore, substituting the value of ID1 and ID2 here, this ID1 and ID2 in this equation, we'll get the relationship between the output voltage in terms of the input voltage. So in this case, we already derived the drain current equation and drain current ID1 minus ID2 in terms of Vn1 minus Vn2, and we must recall that our the difference of output voltage V1 minus VO2 is equal to ID1 minus ID2 R2 times RD. So in this equation, it can be emphasized that we can really get the characteristic of the output voltage in terms of Vn1 minus Vn2 by using the ID1 minus ID2 na equation. So with that, we remember actually first that this ID1 plus ID2 is equal to ISS and ID1 minus ID2. Let's say this whole equation here denotes to a K. And we can say that by solving two equations into unknowns, we can get ID1 is equal to ISS over 2 plus K of 2 and ID2 is equal to ISS over 2 minus K over 2. As can be seen here, if our Vn1 minus Vn2 is very big, there would come a time na magiging malaki pa siya dito. So, this one here would surpass the overdrive voltage, and that is not what we want to do, because we all know that in order for this differential amplifier to work properly, the VO1 minus VO2 must have a range from square root of 2 VOV, the overdrive, to square root of 2 VOV in order for it to still amplify. So now the question is, what happens now if ever our ISS is double? If mas malaki siya, so what would be our characteristic now? So lalaki yung ISS na, we all know that the overdrive voltage defined as ISS, let's say we have ISS mu n COX WL. So if this one gets double, our overdrive voltage also increase. So lalaki yung overdrive voltage natin, and also our ISS increase. So ito, lalaki, lalapad yung overdrive natin. Say, magmo-move yung overdrive at lalaki din yung ISS. If ever, we'll double the ISS. So when we double ISS, our overdrive voltage range would increase, and at the same time, lalaki din yung gain natin, since VO1, VO2 with respect to Vn1 minus Vn2 is malaki, then we'll have a greater gain. The change of output voltage with respect to change of input voltage is malaki na. So with that, yeah, that is good, but the trade-off of that, since our ISS is big, then our power consumption will also increase. So makikita natin na may trade-off siya dito. So now, what happen if kunin natin yung red, in which tanggalin natin to. So yun yung case if our ISS gets bigger. So now what will happen if we double our WL? If we increase this WL here. If increase natin yung WL natin, liliit yung VOV niya. But same pa rin yung ISS. So since same yung ISS, pero liliit yung VOB niya. So, yun. Ayun. So, much steeper siya. Same pa rin yung ISS. So, steeper lang. So, since magiging steeper siya, if this is steeper, then the gain will increase. Malaki na yung gain kanina pero hindi gaano kalaki kasi malapad din yung VOV natin. But here, our VO1 minus VO2 is still the same, but yun, yung VN1 minus VN2 natin maliit. So, mas magiging malaki yung ratio niya. So, in this case, when our WL is increased, our gain also increase. But, our VOB, yung input voltage natin, yung VN1 minus VN2 natin, liliit. So, now, what happened if, ano ba? Yan yung lalakihan. What if our so now yeah, that is the case whenever we change the WL and the ISS value, when the effect of the output voltage difference with respect to input voltage of our differential amplifier. Now let us look at this equation here. As we observe, as you can see, we have this square value here, this Vn1 minus Vn2 squared. So this connotes or implies a nonlinearity of the equation since this is in squared. So whenever our Vn1 minus Vn2 square here is very much less than for ISS mu and CUX WL. Masyado itong maliit. Let's say this is so maliit. And we know that this square root of okay, so in order for us to get the value of Vn1 minus Vn2, let's square root both sides. So we'll have Vn1 minus Vn2 square root of 4ISS mu n CUX WL. And we know that this one is our overdrive voltage here. So we can say we have 2 square root of ISS mu n CUX WL, in which this case is our overdrive. So we'll have 2 times overdrive voltage. So when our Vn1 minus Vn2 is very much less, masyado na siyang maliit. So, maliit na siya na value na dito na siya. So, we'll need to get another analysis in which is the small signal analysis. So, we'll try to get the small signal analysis later of the differential amplifier in the next lecture.